Hey guys, welcome to 5.3 impulse graphs, 5.2 and 3. And so we're going to look at how to graph the impulse or change of momentum. Graphs really help us out. They tell us lots of things. We can tell lots of information by looking at a graph. When we're graphing things, we can look at things in a non-constant force. And so everything we've been given has been a constant force. But obviously forces aren't always constant. Most of the time they are changing over time. So we'll start off with a constant force. So I'm going to sketch the graph here. On this one, for areas above the x-axis, this is the time. We assign a positive value for the impulse. So much like displacement and work, this positive area means a positive change in momentum in this case. So areas below the x-axis, we assign a negative sign. The area under the force time graph is force times time, which is exactly how we define impulse. So the area under the force time graph is impulse. The slope of the momentum versus time is the net external force. So depending on what we're being asked to graph, the slope is going to be either the net force, if we're graphing momentum versus time, or the area, which is going to end up being the impulse. So I have a first example here. It's pretty straightforward. We have an object of a certain mass that experiences a net horizontal force in the positive x direction and begins moving, using the force time graph to find the net force delivered by the net impulse delivered by the force after it has been applied for 6 seconds. And so we see that it starts at 0, goes to 2 newtons up until 2 seconds, remain constants for 2 seconds, and then decreases back to 0 for 2 seconds. So we could use the area of the trapezoid equation to find the area under the curve. Some of us may not remember the area under the curve formula for a trapezoid. Remember, we use J for impulse, or I, kind of depends on which book you're using, so we're using J in this case. The other thing you can do is add all of the areas up. So I have a triangle, and a square or rectangle, and then a third triangle. And we would add all those up, and we should get the same 8 Newton seconds for impulse. Here's one that has some negativeness to it. So we have a 2 kilogram object at rest experiencing a net horizontal force in the positive x direction and begins moving. Using the force time graph to find the net impulse after it has been applied for 6 seconds. So we divide the total area into 2 triangles and find the area under the curve. Since triangle 2 is under the time axis, we'll use the negative impulse. And when we add those two things up, we end up getting 0. We get a total net impulse of 0. All the positive stuff minus all of the negative stuff. So then we're going to talk about conservation of momentum and the types of collisions associated with them. So in our last unit, we learned that energy is conserved in a closed system. And like energy, momentum is a conserved property of nature. It is not created or destroyed in a closed system. In an open system, however, work is done to change the energy of a system. Impulse changes the momentum of the system. And so what basically we're saying is the impulse is due to some net outside force causing something to happen. So to apply conservation of momentum, what we like to do is we take snapshots of the system before and after an event. So a really good example is to use these two, a before and after of a bowling ball hitting the bowling ball pins. Obviously before, the bowling ball hasn't hit them yet. And afterwards, something happens, and we can calculate the changes of that. So a quick a quick rehash of our momentum change and momentum. We have initial momentum plus J, which is the impulse, is the final momentum. A net external force acts on an object. It imparts an impulse J and therefore changing its momentum. So all of this is kind of just saying the same thing. If there's no external force on the system, then the momentum of the system is conserved. Initial momentum is equal to final momentum. A Newton's cradle is a great example of this. It's an animation, of course. But we have just the one ball hitting the other ones, and notice not all of them are moving, just the one. If we were to move two would hit the ball on the left side, and two would come out the right side, and so on and so forth. The forces of the ball striking and being struck are internals to the system, so there's no external force and no impulse. Momentum is conserved in this case. The conservation of momentum is useful because we can analyze the interaction of objects when the forces between the objects are much greater than any external forces acting on them. That's really just a thing to say that we don't really care what the things look like. We treat them as point masses, and their motion is described by their displacement, velocity, and acceleration. We use the object model, that's what that's called. So objects in a closed system can interact with each other in two different ways. They basically collide, or they can explode. They can stick to each other, or they can explode or push apart. So we kind of have a disclaimer here. An explosion in physics is much less exciting than it is in chemistry. Typically, what we say explosion is we have a spring being released, or an object is being separated from another object. That's really all that means. So types of collisions and explosions are classified by the way energy changes or does not change form. Inelastic collisions, which means some of the kinetic energy is turned into something else. The total kinetic energy of the system decreases. We have elastic collisions. Two objects collide and bounce off of each other while conserving all kinetic energy. Energy is not transformed into any other type. And then when we have explosions, once again, we talked about that a second ago, the total kinetic energy of the system increases somehow. So stored energy is released in some way. So we have two types of inelastic collisions. In both cases, kinetic energy is transformed into other things. A perfect inelastic collision, two objects collide and stick together and move as one mass with the same velocity. General elastic collisions mean inelastic collisions, two objects collide and bounce off of each other. Their final velocities may be different depending on their masses and initial velocities. Then we have elastic collisions. In elastic collisions, the initial kinetic energy of the system is equal to the final kinetic energy. The kinetic energy of each of the objects can change, but the system kinetic energy does not. There's no really any such thing as a completely elastic collision. There's always some kind of energy loss or transform in some way. Sometimes so little energy is transferred that we can pretend or estimate their elastic collisions. So we have the ideal gas law. We are assuming certain things when those molecules and atoms hit each other. We assume they are elastic collisions. Super bouncy balls, ball bearings on steel plates. It's Olympics. You guys have seen the curling rocks hit each other. Those are roughly elastic collisions, things bouncing off of each other and transferring almost all of the energy. So firecracker is obviously an example of an explosion. Fireworks, the chemical potential energy inside is transformed into light, heat, and sound. A cart with a compressed spring is a good example. When the spring is against a wall, it is released. the cart starts moving and converting all of that elastic potential energy into kinetic energy and sound. How can these be elastic or inelastic collisions? Last thing we'll take a look at here is this chart. So obviously fill this chart out, but it's a really nice way to pull everything together. Momentum is always conserved in these cases. Always conserved. The initial momentum is equal to the final momentum, whether or not there is a change that's happening. However, kinetic energy is not always conserved. In some cases, you will increase the energy. In some cases, you'll decrease the amount of kinetic energy. When things stick together, we tend to lose energy somehow. So understanding how this chart works and knowing what type of collision does what is going to be pretty critical to how we solve our questions. All right, thanks for watching. Make sure we followed along on those notes. Make sure you get filled out, and I will see you guys later. Thanks. Bye.